We'll go ahead and get started. In the name of the Father, the Son, and the Holy Spirit. Amen. Loving God, we pray that you will bless us as we reflect on the origin of the universe. Open our minds to contemplate the vastness of the beauty of all creation. We ask this through Christ our Lord. Amen. So there's two things that I wanted to look at today. The first is the origin of the universe, and in particular with regard to the possible theories for explaining the origin of the universe, and asking and hopefully answering to a certain extent what are some of the more cogent arguments for the origin of the universe. The second thing that we want to look at is the high degree of improbability that there would be an anthropic universe. And what I mean by that is a universe that is open to the possibility of human, or any life for that matter, existing. So we're going to look first at the universe in general. How vast is the universe? Well, if we are to consider how big the galaxy is in which we exist, well, it's about 10 light years. Here to the sun is about 10 light minutes. From here to Mars is about 15 light minutes. In other words, if you're traveling at the speed of light, you will reach the sun in about 10 minutes, and you'll reach Mars in about 15 minutes. Now, I heard recently that they are looking at doing an excursion to Mars. Does anybody remember how long they expect that to take by spaceship? I think it was 2 years to get there. Yeah, a year and a half to 2 years is what I've heard. And that's one way. So you get there, you do your work, and then you come back. So that gives you an idea of how far away Mars is, and then how fast the speed of light is. So it's a really, really fast, high number. I think it's 3.0 times 10 to the 8 meters per second. Okay, so the closest star to Earth, not including our own sun, is 4 light years away. So traveling at the speed of light for 4 years, you would reach the second closest star to Earth. And how vast is our galaxy alone? Well, we think 75,000 light years in diameter. And then there's not just, in our galaxy we believe that there are, 100 billion stars in our galaxy alone. And then how many galaxies do we believe there are? 100 billion galaxies. So as many stars as there are in our galaxy, we believe that there are that many galaxies in the universe. So how many stars are there in the universe? Well, I'm not sure we have a real number for this. It's 1 times 10 to the 22nd. That's how many stars we think are in the entire universe. So the universe, we would say, is quite vast in terms of its size. Now, if we were to estimate the number of atoms in the universe, we'd say 10 to the 79th. So 10, to the 79th. How you would express that? Well, it's 1 times 10 to the 79th. So, yeah, very vast. Anyway, kilograms in the visible universe. Well, we believe 10 to the 53rd kilograms. So and this is visible mass, not including dark matter. And then finally, how old is the universe? Well, we believe, based on our current calculations, that it's about 13.7 billion years old. And remember that Earth is about 4.54 billion years old, and human life, we've been around for about 200,000 years. Homo sapiens sapien life has been around for about 2 million years. So that just gives you a little bit of an idea of the scale of things. And it is quite vast. Now, we might ask ourselves, well, how do we estimate how old the universe is? And according to what model do we estimate that the universe is 13.7 billion years old? And I'm basing it on the standard Big Bang model of the universe. So we will look at that then. And that's based on recent developments in physics. And when I say recent developments, I'm talking about in the last 100 and 120 years of development. In particular, with our understanding of light and our understanding of space and time. So, we have Einstein in particular to thank for that, above all, him to thank for our understanding of both, really light, our understanding of gravity, and relativity, the theory of relativity. So, we understand light to be both a particle and a wave. And Einstein calls this a photon. That's a packet of energy. And it, again, is both a particle and a wave. We can't explain it as either exclusively, but both. And we also say that if there's no medium, well, there is no medium the light travels in. Sound, for instance, travels in the medium of air. And when you make a sound, we can hear because of the vibration of the air. If you're in space and you try to make a sound, you don't hear anything because there's no air in space. And so you can't hear anything because those waves have no medium to travel in. But light does not need a medium. It simply travels as a photon. And the other thing about light is that it has a constant speed in a vacuum. And as I've already said what that is, it's 3.0 times 10 to the 8 meters per second. All right? So that's the speed of light, which is a constant. And this is something that's very important when we're talking about something like the theory of relativity. Now, when we think about the theory of relativity, it doesn't mean a whole lot for us who are here on Earth. But if you're talking about dimensions of space, then the theory of relativity becomes significant. So the theory basically says that the speed of light is the same for all people. For not all people, but from all perspectives. So whether you're on a spaceship that's moving a fraction of the speed of light compared to Earth that is moving relative to other objects, the speed of light is going to be the same. And so it tells us something about the dimensions of space and time. In other words, space and time are actually really co-relative. They relate with each other. So rather than looking at space as though it were something of a three-dimensional world, we look at space in the dimension of time. And time itself is not something that is linear, but rather co-relative with space. So that's a little bit crazy, I know, and it really is quite upsetting to our way of understanding the world, especially in reference to how we understand it in terms of classical physics and our current experience with the world. This is just an example image. If a person gets into a spaceship, they travel really, really fast. We're talking about fractions of the speed of light fast. Obviously we're assuming that such a thing could happen, which, right now we don't have the technology to be able to do that. But if you could, and a person were able to travel at a fraction of the speed of light, this is where it's important, relative to another person, relative to another planet or a person on a planet that is relatively stationary, the person in the spaceship is going to age slower than the person who is on the planet. So, why that is? Because the speed of light does not change in relationship to the person, the moving object, all right? Okay. This is all important for understanding what we're going to get into momentarily. The first person to come up with the theory of the Big Bang, it was Monsignor Lemaitre, and he did this in 1927. He published what was really the first rough estimates of a Hubble constant. Based on observations of the celestial bodies in the universe, it was discovered that everything relative to Earth seems to be moving away from us. And they used their understanding of light and basically to determine this reality. It's surprising to a lot of people that it was a priest that came up with the Hubble constant. He was the first to come up with this Hubble constant. The difference between him and Hubble is that he published in a Belgian journal in the Belgian language rather than in an English journal. So Hubble becomes more famous than Lemaitre, even though Lemaitre is the one who first comes up with this theory. So basically what we know is that if an object is moving away from us, it has a red shift in light on the spectrum of light. In other words, watch the cursor. If an object is moving away from us, then that object is going to shift towards the red end of the spectrum. If it's coming towards us, it's going to shift, the light that comes towards us is going to shift towards the blue end of the spectrum. Again, this is due to that constant speed of light. So, why is all of that important? Well, this is an observation that was made. The celestial bodies in the universe tend to be moving away from us, okay? Now, looking at another element that supports this notion of a Big Bang theory, we have something called cosmic microwave background radiation. And Arno Penzias and Robert Wilson discovered, by accident, cosmic microwave background radiation. And for their discovery, they received the Nobel Prize in 1978. But what's significant about this background radiation? Well, when we look at what it consists of, this background radiation, well, I had a slide here. I'm not sure that I have one anymore. But we believe that about 1% of this, or a percentage of this cosmic background radiation is due to a large event that happened at the origin of the universe. So maybe this light energy originated with a huge event, which we call the Big Bang event. Now, when we are looking at the trajectories of the movement of the celestial bodies, it becomes apparent that there's an origin, a place where all of this stuff seems to have begun. And mathematically, it's calculated as a singularity, a place of origin, where the Big Bang starts and everything expands from there. And if you're to do certain calculations, you can determine, oh, well, this came from over here, this one's over here, but they probably began at about here. And then if you consider the time and all of that, you can basically come up with a fairly accurate awareness of where it began, not only in space, but also in time. And so that's the idea behind the Big Bang Theory and why they are or how they're able to come up with some explanation for where it begins. Okay. Now, as I said before, I don't think that there's really any question that there was a Big Bang event, that everything was condensed into an infinitesimally small, dense existence or matter, and that it expanded from there and continues to expand today. Virtually no physicists are going to question the truth of that. The question is that the origin of the universe? Or is there something that exists before that, something that precedes this singular event? And there are a number of different opinions. Some argue that the Big Bang is the beginning and here are the reasons why it must be so. And others argue, well, it's possible that there might be some other Big Bang, some other event that precedes the Big Bang event. So, we've got the standard Big Bang model. This is the origin of the universe. Everything begins with that. Another model is a bouncing universe model. In other words, it's kind of like an oscillating universe. The universe expands, it slows, it eventually contracts and comes down to an infinitesimally small and dense existence again, and then it expands. So bounces back and forth, expands and contracts. Another view is in an eternal inflationary model. In other words, the universe has always been expanding, and it will always expand, and it will never not expand. That's not a very strong argument, considering that we see the limitedness of that, right? We see that the universe has a finite, singular origin. So this isn't such a strong view, at least with regard to the evidence. Another argument is that there are many dimensions to the universe, and that this is just one dimension, and that perhaps there is some window into another dimension that occurs with the Big Bang, and that, you know, a different universe with different rules of physics and different rules for governing the physical world. Well, there's a lot of physical evidence that suggests that the origin of the universe begins with the Big Bang and not any other model, especially an oscillating model. The number one reason for this is based on the second law of thermodynamics. Does anybody have any study of science, especially some of the harder sciences like physics or chemistry? Yeah. So the second law of thermodynamics is a law that governs entropy, which is the disorder of a system. And it basically says that entropy of a closed system is always either increasing or staying the same, but it does not decrease. So entropy is a measure of disorder. It's saying that in any closed system, disorder is never going to decrease. It will always increase. And what are some examples of this? Well, you might think of the air molecules in a spray can that have been condensed into a spray can. Those air molecules want to escape. And when they escape, there's no explanation for, or really chance, that they're going to come back into that canister in the condensed manner in which they are. So disorder is always increasing. Similarly, we might take a coffee cup that has been heated up. The heat energy is going to disperse throughout the environment. It's going to get closer and closer and closer to the temperature of the room in which the coffee cup exists. It is not by nature going to heat up, right? Certainly we can heat the water up, but if we do that, then we're burning energy. We're using energy. Certainly the air can get into the canister, but we have to use energy to do it, okay? So that first principle for why a Big Bang Theory model is a strong model is based on the low entropy that we have in the environment. How low of a chance is it that we have so low of entropy that we did at the Big Bang? Well, and this is, of course, somewhat of an estimate, but Penrose, another physicist, did an estimate and concluded that the chance of the universe having as low entropy as it did at the Big Bang was 10 to the 10 to the 1/23rd to 1. In other words, ridiculously small chance that it would be that disorder, that low of entropy. So in other words, not getting too caught up with the math. The entropy was so low that it was an extremely, extremely low amount of entropy, an extremely unlikely amount of low entropy. So if we are to consider other theories, oscillating theories of the universe, entropy doesn't decrease even in an oscillating model. It's still going to be the same. So if we were to advocate the view that the universe oscillates back and forth, how is it that the universe at the Big Bang had such an incredibly low entropy? There's not really much of an explanation for that. All right. One of the ways that we know that this low entropy exists, again, has to do with that background radiation we were talking about that Wilson and Penzos discovered. Okay. In other words, that radiation, that microwave radiation, is itself a form of the entropy or energy of entropy. Energy due to entropy. Anyway. I'm going to tell you now, my understanding of the physics is not that great. I've had physics, I've studied it, but this is not my strongest suit. My stronger suit is probably in the evolutionary biology field. Yes?
Is the entropy you're talking about the same thing as the expansion? When you're talking about the expansion, I mean, it's because they can tell that the light's moving away at a steady rate. Are the microwaves something they hear, they measure by sound, and since it's steady, it goes away?
Well, so that's a good question. Microwaves are light, so they measure it by measuring the light. Now, it's light, but it's not on the visible light spectrum. So when we look out into space at night, all we see is black, mostly, right? With a few little lights of starlights, right? That give off what we would consider to be in the visible spectrum of light. Microwave light is extremely, extremely low energy light. So, in fact, it's probably one of the lowest of the energy of the light sources. Radio waves are lower than microwaves, but it's a low energy light. I'm just looking at this light spectrum right here. We have the stronger light forms, gamma rays, and then microwaves. So what happens is that light, photons, will bump into matter and they will excite electrons. And when they excite those electrons, they stay in an excited state. But then eventually, those electrons may go down into a lower state of energy, and they may release a photon. And when they do that, time and time and time again, eventually, slowly but surely, energy is released, and those photons become a little bit weaker, and eventually move into that range of the microwave light. If you don't get it, don't worry about it. I hardly get it. I don't even know that I really get it. Okay. If you're asking in part, is this microwave radiation a measure of entropy? In some ways it is, yes. Okay. All right. So we've got the low entropy paradox, in other words. Another argument has to do with this, and that is, it's basically called Carroll's paradox, and this is the individual who came up with this theory, a physicist, John Carroll. Now, I believe he came up with this theory in relationship with oscillating systems, but essentially where it is significant for what we're talking about, it is to say that systems do not by nature become extremely ordered as we see them, okay? So to say, this kind of relates somewhat with our understanding of low entropy, but it also relates to the fact that when the universe was extremely dense and small, it was extremely, extremely ordered. And things do not, by their nature, become more and more and more ordered. And one explanation or law that explains this is called Carroll's paradox. Another argument is that, and this again relates to entropy, if you have a bouncing universe model based on the entropy that is produced with each expansion, eventually you will get a universe that expands infinitely. Because the more a universe expands, the more entropy is produced, the more energy that keeps that universe from being able to come back together. All right? And so that eventually you're going to have, in other words, a limited number of expanding or oscillations, expansions and contractions. That's basically what that says. How limited? Well, just depends. All right. Let's look at one last thing. This is another important theorem, or helpful theorem, I think. And it basically says that for any possible universe with an overall positive Hubble constant, in other words, for any universe that is expanding, like our universe is, there must be a finite moment of beginning. Now, why is that? Or how is that explainable? Well, again, it's kind of related to relative physics. The example given is that essentially, I don't even know, let's see. As an object gets further and further away, it from our appearance is going to slow in the context of an expanding universe. So that if you are to look at it regressively, it is to say that something was going really, really fast. But we know that the limit of speed that it can go is the speed of light. And therefore there must be a limit. All right. So, why is it that the guy whose book I read, Robert Spitzer, argues that standard Big Bang model is the origin of the universe? All of these reasons. Extremely low entropy, Carroll's paradox, extreme fine-tuning, Tolman's limit, and the BBG theory, which we've already talked about. So, very strong argument against any other origin of the universe. I think entropy is probably the strongest, most coercive argument. Does life originate naturally? Will it come into existence by nature? I don't know. But again, I think that just based on this argument that looks at the question of the chances of an anthropic universe coming into existence, if we are to consider the chances of the diversity of life that exists, there's a strong argument that there's an underlying intelligible providence guiding what happens.
Because of all the complexities.
Because of all the complexity, yes, and diversity that we have in such a short period of time. In other words, randomness is extremely unlikely. Randomness as a cause for the order of the universe is extremely unlikely. I guess, to be honest with you, it starts with the philosophical question of the pre-Socratic philosophers. Has the world always existed? Or is there an origin to the world? Was it brought into existence? And if it was brought into existence, was it brought into existence by God or by just natural forces? So, obviously, we're kind of picking up where that left off in the philosophical sense, but we're using a lot of the physics to make our argument, right? Which, of course, from our perspective, a perspective with the aid of divine revelation, we believe that God created the universe. So we do believe that God providentially guides the order of the universe. That having been said, it's not necessarily, in fact, it's not at all contrary to nature. Okay? Yes?
Is there any theory that would tell us, from a scientific view, what happens before the Big Bang, how you get there? And Stephen Hawking wrote Brief History of Time.
Yes.
He talks about how that's kind of unknowable to know what happens before that singularity. Is
That's
there
correct.
anything, because, true, like your presentation shows, about the unlikeliness based on probability of how we got here. But even science really doesn't have it, not that I know. Maybe that's what.
No, that's exactly right. And that's the whole thing. Like, in some ways, that's the whole purpose or attempt of physics to come up with to develop a coherent theory of working the theory of relativity in with an understanding of quantum physics. Quantum physics pertaining to the very small subatomic world, the interaction of chemicals and such, and then relativity having to do with the physical explanation and understanding for the cosmic celestial bodies and their movements, gravity and stuff like that. The goal today is to come up with a theory that explains everything, one that is able to bring together in a coherent thought the theory of relativity and the theory of quantum physics. And right now, probably the best effort in that realm is string theory, or string theory. And they're looking at, obviously it's very difficult to know, but they try to understand how things work on a very small scale, what we call the Planck era. And the Planck era is that smallest unit of time after the Big Bang. That smallest unit of time. What was that very small unit of time as it understood? 5.39 times 10 to the negative 43rd, around there? Yeah. Anyway, that's the so-called Planck era, which is what you're talking about. Does physics change? Is physics different? Maybe the physics that guides the so-called macro universe in which we exist today is not the same physics that rules the Planck era. So, in the Planck era. Really kind of crazy stuff.
Scale.
Yes.
On the Big Bang theory, of an exploding star. Are they gaining anything from that to relate to the Big Bang theory?
I'm not sure.
The exploding star.
Yeah. I don't know. Probably, right? I would assume so. Yeah. Again, I got to tell you, astronomy is not my strong suit, but
I just read recently there are 20 mysteries in the universe that are still scientifically not resolved. And just one of those is the heat of the area around the sun. It's much hotter than the sun itself. Now that's just one. That's one. There are 19 others that they haven't resolved. With the Hubble telescope, things like that, we've experienced the different patterns of light, which we can't explain.
sure.
Some are beautiful, and they just don't try those kind of things.
Yeah.
How amazing.
Yeah. Well, and I think that a lot of it is kind of being worked out with an understanding of what dark matter,
Yes.
what impact dark matter has. And dark matter does not emit light. There's no visible, it has dark energy rather, and it acts more like a field. So it has an impact on light, visible light that is, I guess, insofar as it acts as a form of gravity in terms of the interaction with light. So that's how we're able to discover its presence. All right. Thank you guys for your attention.